Hello and welcome to ITN State classes once again. So in the previous lecture, we have seen some linked list operations and how to define a linked list. And we have also seen that what is the use of the linked list. We compare the linked list with array in case of memory. In array, the memory address are sequential, okay, or we can say contiguous. So what is the difference between continuous and contiguous? Continuous means that after 1, 2 will come, then 3, then 4. This is continuous. Contiguous means if integer is taking 2 bytes, then if the starting address is 1, then the next address will be 3. Okay, so this is contiguous. Based on the space, we are saying that the next number will be 3 because this is 2 bytes, then this is 2 bytes. Then we have 5. Okay, so this is contiguous. So in array, the memories or memory allocation is always contiguous. Okay, contiguous. And in linked list, if we have memory, suppose this is our disk and we have some chunks of memory like this. So if we allocate a array sequentially, suppose we have allocated array or any other data structure which occupied this here, and we have allocated some integer pointer here or integer value here, and then we have allocated this one here and this here. So still we can create a linked list out of it. We can allocate this to a node, linked list node, and this can refer to this node, point out to this node in next pointer. This can point out to this node, and this can point out to this node. Like this, basically linked list can be formed. This don't have to be in contiguous manner. Then what is the benefit? We can increase and decrease the size of linked list very easily. Right? If you want to one more node, just point out to the next memory or whatever the memory is available in the whole, whatever the memory is available in the whole memory. You can allocate that chunk of the memory and add it to the linked list node. And you can easily delete also. So you can delocate this one, delete this one. Then you can delocate this one, or you can delocate any of the node. So the expansion and decrease and increase in the size of the linked list is very easy. But in array, if the next address is occupied, you have to pick the whole array. Suppose you want to increase the size of array by 1, you have to pick the whole array, allocate it to the somewhere else where we have size 4 memory available, Okay, so this is the problem with the array. But the addressing in array will take order of 1 because we know the indexes, right? So to identify a specific location, for example, if you want to identify 6th node or kth element in array, okay, that will take order of 1 because we know the address, okay, kth address. We have seen the array addressing. It will take order of 1 time, constant time only. But in linked list, we have to go from first node. We have to start from the first node because we only have the pointer to the first node, okay? Then we have to iterate to the linked list and go to the kth element. Suppose this is the kth element. So we have to go to the kth node here. So that is one problem. Traversing of the linked list will take time. It will take order of n time if we are going to the nth location, okay? So that is the difference between array and linked list. Now let's see some sample programs of the linked list because these programs are very important. We have seen the binary search in the array. Okay, binary search in the array. So suppose we have a array given, which is a sorted array. Binary search is possible in sorted array only. If you know the binary search, you know that why it is possible only in the sorted array. Okay, so suppose we have value like 10, 20, 30, 40, 50, 60, 70, 80. Okay, and we have indexes 0, 1, 2, 3, 4, 5, 6, 7. Now we want to find some element, for example, 40. Okay, node 40. For example, we want to find out 50. Index of 50 element, or we want to identify whether 50 is present in the array or not. So what is our approach? Our approach is simply find out the mid of the array, which is basically 7 divided by 2, and we will take floor of it. So which is 3. So 3 is the mid. We consider 3 as the mid. The left one we consider as the mid. So this is the mid. Now array is sorted, and we know that 50 is greater than this mid. So we can neglect the half of the array. We can neglect means we won't be searching into the first half. We will be searching only in this half. Similarly, again, we will identify it's actually 7 plus 0. First index plus last index. Now the first index is 4. So what is the mid of this remaining array, which is 4 plus 7 divided by 2. Okay, this is the mid. This is the mid. So 11 divided by 2, which is 5. Now we will consider this one. Now we will see that, okay, 50 is actually less than 60. So we can neglect this one, and we will only search in this remaining array. And we find out that, okay, this is the index. So within 3 steps, we can identify the index of 50. If 50 is present, if 50 is not present, we will search all the spaces and we will conclude that, okay, the index is -1. It means -1 indicates that element is not present. This is not actually ideal to return -1. We can return any like any value which represent that, okay, we can represent some character or some index. Generally, we return -1, which is basically less than 0. So it says that, okay, element is not present in the array. Okay, so this is the binary search. Now we have seen the in algorithm part, we have seen the time complexity using some tree-like structure, recursive tree method, and other methods. It took actually order of log n. So what if somebody asks you what is the time complexity in linked list of the binary search? Okay, what is the time complexity of binary search in linked list LL? So what now the main part is at each iteration in the linked list, let's consider linked list. Okay. This arrow represents the pointer. Okay. So we have values like 10 here, 20, 30, 40, 50, 60, 70. These are the values. For example, again, we want to identify 50. Okay. So to find 50, we need to identify first the mid in the binary search, the mid of the linked list. We have only the start pointer. You don't know how many elements the linked list have. Okay. And even if you know the number of elements in the linked list, how would you go to the middle element? Now it will solve many problems. Sometimes it is given in the examination or interview to identify the mid element only. They will say that if number of elements or number of nodes are even, you can return any of the mid. For example, here number of elements are 1, 2, 3, 4, 5, 6, 7. So number of elements are not even. Okay. So let's give them index. In linked list, there is no such thing as index. Still, for make sense of this mid, okay, we are labeling them 0, 1, 2, 3, 4, 5, and 6. So now we know that the middle element is this one. Okay, 3 here, and this is the middle element. For example, if we have instead of 6, we have 7 elements. Here we have actually 7 elements. Instead of 7, we have 8 elements. If we are starting from 0, right? 0. So that is why the index of last element is 7. If 80 is here, then in that case, what is the middle element? Either this one or this one. And in the examination or interview, they will give you that, okay, out of these two, which one to consider as the middle element. For example, they can say you that, okay, left one is the middle element, or you, in the case of even element, you can consider this one as the middle element, or this one. That depends upon your question paper. Otherwise, if it's not given, you can consider any of these two as the middle element. Okay, generally I do like 7 plus 0 divided by 2 and take floor of it. I'm not taking ceiling, I'm taking floor. So automatically this is the middle element, right? If I take seal, 7 plus 0 divided by 2, then in that case, this will become the middle element, right? Now let's consider this as we have only odd number of elements, right? Now we must know the middle element, then only we can start doing the binary search. Why? Because after identifying the middle element, we can locate on which side of this middle element or key element which actually we are looking for. We are looking for this element. On which side of this element lies? 50 lies. Okay. So to identify the middle element, we can give an algorithm, right? If you think about it, we can take actually let me tell you first the approach of the identifying the middle element. Okay. Our approach is basically take 2 pointers. You can pause the video and actually try to figure out what is the best algorithm to identify the middle element in a linked list. Okay. You can pause the video and you can try to identify the middle element. Now I'm telling you one approach is simply start from here, iterate till the end. Okay, iterate till the end and note down the number of elements. Here we will start from here. Okay, this is the first element, this is second, third, fourth, fifth, sixth, seventh. So we have 7 elements. Now the fourth element, 7 elements. Now out of these seven, we can say that okay, the third element, so not the third, actually this is the index, but actually this is the fourth element. The fourth element with index 3, fourth element is middle element. This is one of the algorithm, but this is not the best algorithm actually. This is not the best approach. What is the best approach? We will take 2 pointers. We start from beginning, from S, or you can say start pointer only. We will take 2 pointers here. One is P. Let me use some other color, I think a green color. So we will take P pointer here, which will point out to this one, and Q pointer here, which will again point out to this one. Now this Q will jump 2 times, and this P will jump 1 time in each iteration. We'll iterate till this Q become either null. Okay, till this Q become null, we will iterate. So what happens in the next iteration? Let me clear the board a bit. In the next iteration, or you can say in the first iteration, what will be the position of P? Initially, P and Q both are pointing to the first element only. Okay, both are pointing to the first element. So what is the step 1? Let me write step 1. Step 1 is P is equal to S and Q is equal to S. Okay, so P is pointing out to, this is the pointer, start pointer, Q. We cannot lose, right? So we have to take temporary pointers. These 2 are temporary pointers. Now Q will jump 2 steps. You can assume that we have these many stones. 2 people are standing here, P and Q. Q is jumping 2 steps. At each iteration, Q is jumping 2 steps. So after the first step, the Q will reach here, and P will reach here. And after second iteration, Q will jump 2 steps, right? Q was here. Now Q will come here. Sorry. Q will come here. And P will only go here. Then again, in the next step, Q will jump 2 steps. So Q will go here. And P will come here. So P is going one by one, like from here to here, from here to here, then from here to here, then from here to here, right? P is jumping like this. But Q is jumping, like Q was initially here, then Q jumped here, then Q jumped here, then Q jumped here. So these two persons, P and Q, Q is jumping 2 steps and P is jumping only 1 step, right? Now Q cannot jump further because here we have null. Q cannot jump further. So we can conclude that, okay, this is the middle element. Wherever the P is standing, this is the middle element. So I hope you got the intuition. We are taking 2 pointers. One is jumping 2 steps, okay, which is, we can say, fast pointer. Q is the fast pointer. P is the slow pointer, which is jumping 1 step each time. Now, till the Q reaches to the end, P will reach to the midpoint. Okay. Once Q reaches the end point, P will reach to the middle point. Very simple, right? Very simple. Yeah. Or you can consider a line here. Here we have marks like 1, 2, 3, 4, 5, 6, 7, 8. You can consider these marks like a nodes in the linked list. Now P and Q are initially here. After like first iteration, Q will jump 2 steps. Q will reach here, and P will reach here. Then in the next iteration, Q will reach here, and P will reach here. P is going like 1 step each time, and Q is going 2 steps each time. Now Q will reach here, and P will reach here. Now can P jump further? Q jump further? Like P can jump, right? But Q cannot jump further, right? Because Q will reach out to null only. And there is no pointer pointing out to null, and like there is nothing here, right? There is nothing here. So Q cannot jump further. So P is the middle point here, 4. Now we have even number of elements, and we have considered that left one is the pointer. Left one is the middle pointer. So this is the way. In coding language, this is the algorithm for mid. You will pass the starting pointer of the linked list. You say that, okay, P equal to S and Q equal to S initially. You created 2 pointers, P and Q. I'm not defining pointers here because this is just algorithm, not the code. Okay. Then you say that in while loop, let me try to write the while loop here, because this while loop will be a little lengthy. You say that until Q is not equal to null, and Q next is not equal to null, and Q next, because you are jumping to the next, not only next. At each step, the Q is jumping to the next and next. Okay, not equal to null. Next and next should also not be equal to null. Then in that case, P equal to P next. P will jump 1 node, and Q will jump 2 nodes. Q next. Okay. And P will reach out to the midpoint. So we'll return P. So in the previous approach, we were taking n steps. We are iterating the whole linked list, and we are identifying like how much do we need to go. Again, after going to the whole linked list, you have to iterate one more time to the reach to the middle. So because you are counting the nodes. In the previous approach, you were counting the nodes. Suppose if nodes are 8, then you are saying that, okay, if the 4th node is the middle node, then you are going to the 4th node again. So how many times you are iterating? N plus n by 2 times you are basically iterating. You were iterating actually the linked list. Now here we are iterating only n by 2 times. N by 2 times, because Q is jumping 2 steps each, and we have conditions on Q here, right? We have condition in Q. So it is taking order of n by 2. N by 2 is still order of n. If n is too large, if n is 1 billion, okay, if n is like 2 billion, we are still iterating 1 billion times. So order of n by 2 is order of n only. And order of 3n by 2 is also order of n only. Previously, it was order of 3n by 2. Still, its order is same, but still it's n by 2, not 3n by 2. So that is why this is the best algorithm to get to the midpoint. Now let's go back to the binary search. We identified the midpoint to reach to the to do the binary search, right? So how binary search will happen? You say that okay, BS, this is a start pointer, and I am finding out some element X. I'm in search of this element X. So you say that if S next equal null, means we have only one node. In that case, we say that if S data equal X, we found out a return S. We find the first node as the this. We found out the first node as the node which contains X. Else, we say that return null. Null means X doesn't exist in the given linked list. X do not exist in linked list S. S is the starting pointer of the linked list. Either this is the case, else we are saying that, or there could be one more case. If S equal null, then return null. Before this, we can write here return null. If our linked list is empty, it means linked list don't have any node, we will return null here. The else part we will write in the next page. Okay, where we have more than one node. In that case, we will say that okay, P equal to mid of, not mine, it's mid. P equal to mid of S. The mid algorithm is basically this function we are calling, which is taking order of n times, or order of n by 2, you can say. We are calling this here, okay? This returns this pointer, the mid pointer. So this is returning mid, which is taking order of n by 2. You can say order of n. If P data equal X, sorry. If this mid pointer is equal to, we found out, or we will return P. Else we didn't find the mid element as the our key element. In that case, we will say that if P data is basically greater than X, it means we can neglect the left half of the linked list, left half, like array. Okay, we will neglect the left half. So we say that okay, let's do one thing. Let's call BS and do this P comma X, and we will consider this P as a starting pointer, right? This P as a starting pointer. So basically, okay. We are saying that node in the left half, in the right half, there is no element, so we can neglect right half because X is smaller, right? X is smaller. So if this is the linked list, this is the mid, then in that case we are saying that X is basically smaller than this mid, this element, right? So we need to look only in this half, right? So what to do in that case? We'll say that okay, do binary search only, but before doing binary search, do one thing. Set the next pointer to null. To ignore this half, we are saying that set it to null. Right? Set it to null and call binary search S comma X. Else, we know that now we need to search this X in this half only, this half, right? It's not in this half. Then in that case, search in P comma X, or you can say search in P next comma X, right? So this is our recursive function. Okay. So what we are doing, we are saying that This is our linked list. First, identify the middle element. This is our linked list, okay? And let me label the element 1, 2, 3, 4, 5, 6, 7, 8, and 9. So in that case, what is our middle element? This is our middle element, right? To find out the middle element, we will take order of n by 2 time, right? N by 2 time. Now we will compare our key element x with this data. If x is smaller, then we will search into this one. If x is greater, we will search into this one. To search into this one, we will call the same function by saying that p next equal to null. Okay. So we are saying that, okay, this will point out to null here. And we can again call the same. This is s, right? We can again call s comma x. As if we want to search here, in that case, we will return b as p next comma x. Okay, p next comma x. It means we are only passing this linked list. So this is how we can do this. Either we can using this statement, we can search into the left part, and using this statement, we can search into the right part. Now, the time complexity for this one is, let me type recurrence function. Recurrence relation here. The recurrence relation here is basically, it's if or n is less than or equal to 1. If there is only one node or there is no node, it will take order of 1. Else, it will take n plus n for the mid element, finding out the middle element. Okay, we are calling this mid function, right? Here we are calling this mid function. It is taking order of n, right? So it's n plus p n by 2, right? In the array, it's actually, if you remember, it's actually the effort for finding out the middle element is actually 1, exactly 1. So we will say that 1 plus p n by 2. And the solution for this one is order of log n. I'm not going to solve this again using substitution method or recursive tree method or master theorem. You can solve this if master theorem is applicable. So you can go back in the algorithm part and check that video. Here you can say that, okay, the effort to finding out the middle element is n, right? So if you calculate the time complexity here, it's actually order of n. Here it's order of log n in array, and in linear search, or sorry, in linked list is actually order of n. So that is the you can say benefit of using an array. Searching an element in sorted array is actually far better than compared to searching an element in linked list, right? So instead of applying binary search, you can simply like scan the whole linked list, because the effort is kind of same, and you are not going to waste any space. Here you are wasting space order of log n. Now you say that, okay, where do we spend this this space? This is the space complexity. There is one concept of stack. So whenever we call a function, it's calling, like initially it will call binary search, okay, the start pointer and x. Then it will call binary search some other start pointer and x. Maximum how many times do we call it? How many times? Log n times. Log n times. Why log n times? If there are n nodes or elements in linked list, we'll call it linked list. We'll call it log n times. Why so? Because in case of binary search, the number of function calls could be log n only. Because at each step, we are basically neglecting, or you can say avoiding or deleting half of the nodes, right? Each time we are identifying the middle element, and we are basically considering only half of the remaining elements. For example, in the first iteration, you will consider these many elements. In the second iteration, you are considering these many elements. So the number of calls, maximum number of calls, maximum function calls, maximum function calls of binary search you are doing log n, where n is the number of nodes in the linked list. So these are the number of calls you are doing in maximum in binary search. And for each call, there is a reference to it in stack. So I explained previously that we have two kind of space. We have two kind of spaces in our program or compiler, you can say. So whenever a program executes, it occupies two spaces. One is heap, another one is stack. Stack is for the function calls and local variables, right? It's for the local variables. And heap is for the data structures or the memory that we allocate at runtime. Whenever the program is running, if you do malloc, calloc, and whatever memory it allocate, because whenever that line is getting executed, okay, which is called runtime, at that point, it will occupy heap space. So we have two kind of spaces. Remember this, heap and stack, right? So stack will take and programming space also, programming code, which is static memory, which will be allocated at compile time, right? So that is not allocated into the heap. So the function call, how do we know that once this last function call is returned, it will return here, then it will return here, then the first function call will return us the result. It will return us the result. The first function call will return us the result, right? You are not going to make all these function calls by yourself. The program will, at the runtime, they are going to make these function calls, okay? So that is how this stack will. So that's why the space complexity, which is basically the function calls that you are making, it will take log n space. Okay, so we using the binary search in the linked list, we have cleared many concepts. Okay, that binary search won't make any difference. You can do linear search in the linked list because the finding out the middle element is taking too much effort in linked list. Even if you have a better algorithm, still it's taking too much effort. In array, it's just do the addition of the indexes and divide it by 2, find out the floor. That's it. Okay, so that is why binary search is far better in the significance of binary search is only in array. In linked list, it doesn't really matter. You don't have to use the binary search. Now, where do we use the binary search actually? We use binary search, if you remember, in kind of merge sort. Not binary search, but actually we identify the middle element. We do this mid of array, and it will give us the middle element index. Then we call merge sort. Suppose this middle element is P, then we do merge sort. We'll call the same algorithm, merge sort algorithm, on these middle element, right? If you remember, initially we have the whole array, then we divide it into the half. So to divide into half, we must know the middle element, right? And this middle element, to know this middle element in array, it will take order of 1 only. That is why merge sort is successful in array, but it's not successful in linked list. It will take order of n time, right? And how many times can we call merge sort? Like function wise, recursively, merge sort will call n times. So it will take how much effort? Order of n square it will take in worst case. In linked list, it will take order of n square. Okay, in array, it is n log n. Okay. We are not going to call merge sort n times. It's actually log n times. But the effort at each call of this merge sort is actually order of n, because we are merging two arrays, right? We are merging two arrays. Once we call the merge sort, okay, what is the algorithm? First is find out the mid. Suppose mid is p on the array. Then we call merge sort on this array where we pass the if our initial index are like I and j, we'll call merge sort on I comma p, and merge sort on p plus 1 comma j. Okay, if this is the index, this is our array, current array, I to j, then we will call from I to p. Like we divided the array into two merge sort algorithm, right? If you remember the algorithm part. Then we do this merge algo. We perform merge algo. So this will return us a sorted array. For index I to p, we have a sorted array. For p plus 1 to j, we have a sorted array. Suppose this is a1, this is a2. Then we do this merge algo, a1 comma a2. So what is the effort? Here the effort, if you see that this is n by 2, this is n by 2, tn by 2 actually, it's tn by 2, tn by 2, because we are calling the same function, that is that we are doing tn by 2, and this is n. So our basically this is order of 1. So in array, it's in array. Okay, it's in array. In array, we are doing a recurrence function is like n plus 2t n by 2. And using master theorem, we can see that it's n log n. N log n. Okay, order of n log n. Here it's order of n log n. Okay, order of n log n. But if you consider linked list, here the effort is n actually. Effort is n at each step. At each step, our effort is n. Right? So the merge sort in linked list will take 2n plus 2tn by 2. Okay, that is why it's I think it's wait a second. It's not order of n square. It's also because our recurrence relation in linked list for merge sort is also, if you apply the effort here, only we are doing the extra effort here. Okay, so it is actually 2n plus 2tn by 2. So this is the recurrence relation. Using this recurrence relation, if you solve this recurrence relation, it will also take order of n log n, right? So in linked list and array, both are same. Linked list and array, both are same. Sorry for the mistake. It's not order of n square. It's not order of n square. It's n log n only. But remember this, identifying the middle element is n. So if somebody asks the recurrence relation, it's not n plus tn by 2, 2tn by 2. It's 2n plus 2tn by 2. Okay. In linked list, this is the recurrence relation for the merge sort. In array, it's n plus 2tn by 2. Why the extra n? Because identifying the middle element will take order of n. Okay, but ultimately the time complexity is order of n log n. If you solve this one or this one, it will both give you order of n log n. Now let's move on to the next question, which is like identifying loop in linked list. How would you identify loop in linked list? Okay, if you have something like this, right? Okay, let me create clearly some nodes. A 2000. The address of this is 1000. The address of B is actually 2000. Okay, in the next of A, we are saving the address. It's 3000 here. C 4000. And the address of A, starting address of C is 3000. Then we have D 5000. And A, B, C, D, E. C 6000, G 7000, not 7000, sorry. In G, this is the last node actually, or is it last node? We don't know. Here also we have 3000 here. 3000 means is pointing out to this node. It's pointing out to this node C. Okay. Here the address is basically 4000, address is 5000, address is 6000. So now we have a loop. The linked list, if we try to iterate the linked list, we will keep on iterating. So what we will print, if we want to print this linked list in sequential order, we will keep on printing like A, B, C, D, E, G, then C, D, E, G, C, D, E, G. Okay. This will keep on repeating because there is a loop between these things. Okay. There is a loop here. That is a problem. Maybe it's not a problem. The loop is intentional, but we want to identify the loop here. Okay. Whether there is a loop or not, we want to identify this, right? So what we will do, pause this video, okay, and I will give you a hint. We will use the previous approach, which we use to identify the mid pointer. You can pause the video and write down the program. Okay. Now let's see how can we identify it. We'll use two pointers. Starting pointer pointing to this. We will create two temporary pointers P and Q. Now Q is a fast pointer, P is a slow pointer. Okay. After one iteration, P will reach here, Q will reach here. Okay. After the next iteration, P will reach here, Q will reach here. After the next iteration, P will reach here, Q will reach here. Okay. So right now, this is the position of P and Q. After the next iteration, P will reach here, and Q will go from here to here. And in the next iteration, P will reach here, and Q will also reach here. Like this, okay? So if there is a loop and we are jumping Q for 2 steps and jumping the P for 1 step each, after a while, even if it takes 2-3 loops, after a while, P and Q will point out to the same node. After a while, like they are pointing out to the same node now. Okay, after a while, they will point out to the same node. Okay, so let's illustrate it in another way. Let's try to save the pointers. Instead of like writing down P and Q, it may confuse you. What I'm trying to say here, let's go it like this. Okay, this is 3000. Initially, P is what? 1000. Q is what? 1000. Initially, this is the case. Now, after one iteration, P will reach to the 2000. Q will go to the 3000. Q will go here, right? Because it's jumping for 2 nodes. Okay, P will go in one by one. Okay, 3000. Q will reach to the from 3000 to 5000. Okay, now P will go to 4000. Q will jump to from 5000, it will jump to 3000. Again, now P will reach to 5000 here, and Q will again reach to the 5000, right? Like this. Right? Now we have seen this in like 2 ways, either writing down PQ here and going forward, or you can see, that's why I have written addresses here, right? Addresses here. This is the next pointer pointing out to B, and this is the current pointer. So now you can see that address of both P and Q are same. That is how we can identify loop in the linked list. Writing down the program is quite easy. As I've written the previous code, you can write down for this one also. It's quite easy, right? Now let's see how can we reverse a linked list. How can we reverse a linked list? What do we want? We want something like this. Okay, we have given a linked list S, A, B, C, D, E. We have given linked list like this. We want it like this. Okay, after reverse function, we want it like this: E, D, C, B, and A. We want it like this. Okay. So now, let me tell you the approach first. Then we will write down the program and we close the this lecture. Next lecture we will move to the binary search tree or binary tree. Okay. Let's see what we can do here. Let me try to write down this linked list again. It's A. I'm writing down next pointer address. So address of this current node is 1000, assume it. And here it's 2000. That is why we stored the 2000 here in the next pointer. Here it's 3000. A, B, C. Here we have 3000 here. We said 4000 here, which is a pointer of D. 5000. E, we have null here. Okay, here we have 4000 and 5000. Now, what if that we can do something like this? Okay, because we can go like this only, right? We cannot go back. There's no reverse pointer here. Okay, so tomorrow I will discuss doubly linked list and circular linked list also. Then only we can go to the like tree-like structure. We can go only in forward direction. So instead of going back and try to reverse the linked list from here, we will try to linked list. We can only reverse the linked list from here only, right? From here only. There are few ways, either to swap the data. Okay, either to swap the data, keep on swapping the data, or what we can do, we can do it like this. Okay, in the first node, we will go to next node. Okay, we will save like P and Q. Now we can save Q next, the next of Q in some pointer K, right? Which will save Q next, so that we can move here like P here and Q here in the next iteration. Our approach is, right now we are standing at P and Q. P is the first node, Q is the second node. We can make this one as null. And we can make this one, instead of 3000, we can make it as 1000. So this link will break and it will point out to here. Right? We can move forward like this. Now we can move PQ like this. P here, Q here. Using K, as we have already saved the next of Q. So Q can move like this, right? And now P don't have to do anything. That null is only for the first node. Q can break this link and K will move here. Q can break this link. Q can point out to this node. Then we will move PQ. Again, K will move here. This will point out to this node. And again, we can move like PQ here. Now, whenever we are moving the pointers, we have seen that we saved the Q next in a temporary pointer. Okay, and we save this, then we moved the Q next to the P. Okay, so this is the back pointer. Then we have to move PQ to the next step, right? Right now, it was like this, right? Using this, we made it like this. We break this node and we made it like this. And this was broken and pointed to the previous node in the previous iteration. We made it like this, right? Now we have to move further. So what do? We do like P equal to Q and Q equal to K and K equal to K next. So we have taken 3 pointers and we are moving these 2 pointers one by one and making these links reverse. And whatever is the last node, we make it to the S. Okay, now these links are reversed actually. Okay, these links are reversed. Now you can look it from this side, looking from this side. Your eyes should be this side. Okay, you can look it from this side, and you can make it like this. Okay, these links are like this. Let me write a program for this also. Reverse S. This is reverse. Okay, reverse S. How can we write? We will take 3 pointers where this K will point out to, initially it will point out to S. Okay, to the this initial pointer, and P and Q will point out to null. Okay, then we say that while K is not equal to null, we will do P equal to Q. Remember this, what did we did here? We made P equal to Q, Q equal to K, and K equal to K dot. Okay, P equal to Q, Q equal to K, K equal to K next. And then we reversed it. Like we said that, okay, Q next. Instead of pointing out to the next pointer, now point out to the previous pointer. Which is the previous pointer? P is the previous pointer. If you don't understand it, try to visualize it. Write an example. Try to iterate P, Q, and K. Try to iterate P, Q, and K. Okay. So initially, this is the case. This is K. P and Q are null here right now. Then K will move here. Okay, and Q will move here. P will be still null. So that initial pointer can be made to the null, point out to the null. Then what will happen? After this iteration, K will move to, again, K will move to the next pointer. K will move here. And P was null, right? So P will come here, Q will come here. So that Q can point out to the P. See, Q is pointing out to the key. Q dot next equal to P. Q is pointing out to P. Then K will move here. And Q will move here. P will move here. And again, Q will point out to the P. So this is the algorithm. This is the algorithm. And at the end of it, what we will do, we will say that, okay, S equal to Q. Q reaches here, so we point out S to the last point. Okay, this is how we can make it. So this is the algorithm. If you didn't understand it, write down the step, try to iterate it in your notebook. Okay, thank you all for joining. That's it for today. And tomorrow we will see what is the drawback of linear linked list, because we can move only forward. So there is a concept that at each node, let's make a link to the previous node also. Okay. So which is called doubly linked list. So in doubly linked list, what do we do? Doubly linked list. Struct node int data. For example, our data is of type int data. Struct node star. We have a next pointer, right? In linked list, in a single linked list. And in doubly linked list, we have a previous pointer also, right? Struct node star 3. So whichever program we did, each time we need to maintain only this next linked list. Now we also have to maintain this previous pointer also, right? So this is how we can move back and forth. Now we have pointers like this. Not only this, we have pointer like this also. Now we can go in this direction as well as in this direction. Okay, so deletion and these things will be easier. And reverse of the linked list doesn't really make sense because we can move in the both direction. Then we have circular linked list also, where at the last pointer we are pointing out the first node. Okay, so this is the circular linked list. This won't point out the null. This node structure will remain same as the doubly linked list, and in the circular linked list, we point out the last node to the first node. So make any one of the node as the start pointer. It doesn't really make any difference because it's circular, right? In circle, there's no start and there's no end. And we will see some program of it Then we will move to the tree-like structure. So I will try to give you some brief description about circular because it's very similar to our linear linked list. Just we need to maintain in each program. Not only we need to maintain this one, right? Not only we need to maintain this one, we need to maintain this one also, the previous pointer. Thank you all for joining. That's it for today.